Good day. Today we're going to see 8 proofs of the sum of the monotonic divergent series of natural number. 1 plus 2 plus 3 plus 4, etc. equal -1 over 12. Proof number 1, generating function. So always a good start to when we work with divergent series, to have a look at the generating function that generates the divergent series. If we know the value of the generating function, we will have the value of the sum of the divergent series. So let's start with the well-known power series formula below, 1 over 1 minus x. That's the expansion of the powers of x here. Let gf not g of f of x, gf, one word, as the ordinary generating function for the monotonic divergent series of natural number. What is gf of x equal to? Let's open the toolbox and remind ourselves of the few derivatives. The derivative of x to the n is n times x to n minus 1. If you apply that formula for n equal -1, we have the derivative of 1 over x, which is -1 over x squared. And if you replace x with 1 minus x, you have the derivative of 1 over 1 minus x, which is equal to 1 over 1 minus x squared. Again, the minus sign which is in front disappeared because we apply the chain rule and then multiply by the derivative of what is inside the bracket, 1 minus x, which is -1. So negative times negative becomes a plus. So we have that formula. We plug it here. And then if we have the derivative on the left-hand side, then what is equal to the right-hand side must be equal here to the derivative. So 1, we take the derivative into 0, x derivative is 1, x squared becomes 2x, x cubed becomes 3x squared, etc. 4x cubed. I'm speeding up a bit. Here is the expression. So now what we want to do is to group all those terms per power of x. So you can see there is only one term for each power of x except the first two terms, which are both of them a power of x to the 0 power. So it's like that. We can group them together. 0 plus 1, of course, is equal to 1. X to the 0 is 1, so it becomes 1. 2x to the 1 is 2x plus 3x squared plus 4x cubed, etc. So when we have that expression, let's write it down here and replace or evaluate it x at x equal 1. So generating function at 1 is 1 plus 2 times 1 plus 3 times 1 plus 4 times 1, etc. So it is nothing else than 1 plus 2 plus 3 plus 4 plus 5. It is nothing else than the divergent series or monotonic divergent series or natural number. So we can therefore find the sum here by taking the generating function gf of x and evaluating it at x equal 1. 1 over 1 minus 1 square, which is 1 over 0 square, which is 1 over 0. And that's infinity. So unfortunately, applying the fundamental theorem of divergent series of integers, we conclude that the monotonic divergent series of natural number is unstable. Unstable because the value of the ordinary generating function generating the series, which is x equal 1 in that case, gives us an infinite value, a non-finite value. Therefore, we cannot determine the sum of the divergent series by evaluating its ordinary generating function, gf, with the value generating the series, in that case x equal 1, unfortunately. So it's not a proof. Proof number 2, direct calculation. So is there a way that we can calculate the sum of the divergence or monotonic divergent series of natural numbers directly? There are plenty of ways. Here is one. Let's write down first the monotonic divergent series of odd numbers. Let's open the toolbox to see what that value is equal to. In sigma notation, the sum from n equal 1 to infinity of 2n minus 1. Minus 1 because we start numbering from 1, not from 0. So 2n minus 1 is equal to 1/3. So we can plug 1/3 here. Then the sum of the monotonic divergent series of the constant 1 plus 1 plus 1 plus 1 to infinity like that, it's equal to -1/2. So we can plug the -1/2 here. And then when we have those two divergent series with their values here, we can do the sum. So the sum of the monotonic divergent series of odd numbers plus the sum of the monotonic divergent series of the constant 1 is equal to the monotonic divergent series of even number. That's pretty straightforward. 1 plus 1 equal to. Very important to sum column by column, terms by terms. 3 plus 1 equals 4, 5 plus 1 equals 6, 7 plus 1 equals 8, etc. and so forth. 11 plus 1 equals 12. And then if we do the sum on the left-hand side, term by term, the same will happen on the right-hand side of the equal sign, which is the sum of the sum will be equal to the sum of the two divergent series. So 1/3 plus -1/2 is equal to -1/6. So now we have the sum of the divergent series, monotonic divergent series of even numbers. So let's multiply by 1/2 or divide by 2. So multiplying by 1/2, we get to the sum monotonic divergent series of natural number. And then, of course, if we multiply by 1/2 on the left-hand side, we will multiply by 1/2 on the right-hand side to conserve the equal sign, and it will become -1/12. So in sigma notation, we have the sum from n equal 1 to infinity of n, the natural numbers, is equal to 1/2 of the sum from n equal to infinity of 2n minus 1, that's the odd numbers, plus the sum from n equal 1 to infinity of the constant one, 1 plus 1 plus 1, etc. So the first part is 1/3, we've seen it. The second half is -1/2, we plug it here. Let's not forget the 1/2 in front in factor, and then we have 1/2 of that expression, which is -1/6. 1/2 of -1/6 is of course -1/12. And that's it. We have established the proof of as a direct calculation of the sum of the monotonic divergent series of natural numbers. Proof number 3, intercept function. So what is an intercept function? We will see just now. Step number 1, let's calculate the partial sum of the monotonic divergent series of natural number. So here's our divergent series. Partial sum, the first term of the sequence of partial sum will be equal to the first term of the series, 1 equal 1. Then we sum the second term, give us a 3. Then we sum the third term, plus 3 equals 6, plus 4 equals 10, plus 5 equals 15, plus 6 equals 21. Okay? Step number 2, we express the partial sum Sn, n being the index of the sequence of partial sum, uppercase n, where lowercase n is the index of the series. So let's express the partial sum S of n as a closed form expression. So the sum from n equal 1 to uppercase n of the natural number, the first n natural number. Let's go to the toolbox. We know that result is n times n plus 1 over 2. So we plug that result here. Step 3a, we calculate the intercept point h at n as a half sum of two consecutive partial sum. So again, h of n equal arithmetic average of consecutive partial sum s at n minus 1 plus s at n. So the first expression n becomes n minus 1, n plus 1 becomes n, divided by 2, so the 2 becomes 4 at the denominator, plus s half of Sn, which is the same expression divided by 2, so n plus 1 over 4. We can see n squared over 4, we have it twice, so therefore we have n squared over 2, and then the n over 4, we have negative quarter of it, and plus a quarter of it simplified. So here we have made an implicit assumption here. We are numbering our divergent series from the index n equal 1, and therefore the sequence of partial sum from uppercase n equal 1. So what is the value s at n minus 1, where n equal to 1, so at s0. So we assume, because it's before we start here, we assume it's a 0 here. Assume s0 equals 0. Then step 3b, we express the continuous intercept function h of x by replacing the discrete variable n by the continuous variable x. So simple, we write down the intercept formula, h of n equals n squared over 2, and we replace n with x. This time x is a continuous on a real variable. So we run out of board, let's scroll down to the board below. Here it is, more space. So we go to step 4 and we evaluate h of x where x equals 0. So h of 0 equals 0, 0 squared over 2 equals 0, that's obvious. Therefore, the sum from n equal 1 to infinity of n, which is the sum of the monotonic divergent series of natural numbers, is equal to h at 0 projected onto q, in case it's not a rational number, which in that case, of course, it's 0. 0 is rational, so once after projection, it remains 0. So the sum is equal to 0. Well, not quite. It's not the correct sum. We have a problem here. We need to take the adjusted intercept function for the monotonic divergent series of natural number. And that adjusted intercept function is the parabolic function h of a, h sub a for adjusted, of x. It's -1/12 plus x squared over 2. If we now evaluate this function at x equals 0, step 5b, what do we get? H sub a at 0 is -1/12 over 0 squared over 2, which vanishes. We are left with -1/12. And finally, this is the sum from n equal 1 to infinity of all natural numbers. It is the intercept, the value of the intercept evaluated at 0, or the intersection of that adjusted intercept function with the vertical axis after projection on Q, which is -1/12. Again, that is a rational number, so there's no need to project. Let's just keep that in mind as a general rule. And that is indeed the value of the monotonic divergent series of natural number. Partial sum integral, like I just mentioned, that PSI is as follows. Calculate the partial sums, 1 plus 2 plus 3 plus 4, etc. We went through it, so I'm not going to repeat. It's a sequence of triangular number. You're familiar with that. Express the partial sum Sn as a closed form expression. We've seen it before. The sum from n to uppercase n of the natural number is, I open the toolbox again, but we've seen it already, n plus 1 over 2. Here it is. N being a discrete variable. So we express the continuous partial sum S of x, x being real this time. So it's simple, we replace the x in the expression. We've seen that as well. We calculate the PSI. So what is a PSI? What is the definition of that partial sum integral? So it is the integral from -1 to 0 of the continuous partial sum Sx dx, x being of course the variable of integration. So let's have a look. We can take the 1/2 in front. We factorize that one. 1/2 of the integral from -1 to 0 of x plus 1. Knowing the integration of x to the n is x to the n plus 1 over n plus 1. Because we have born of integration, we can drop the constants. It will cancel each other out. So we have 1/2 of x cubed over 3. That will give us the x squared. And x squared over 2. That will give us the x term. From -1 to 0. So let's replace in the expression. 0 comes here. -1 comes there. That one are gone. It's only 0. We are left at this one. 1/2 -1/3 is 1/6. So -1/2 of 1/6 is equal to -1/12, which is what we are after. So therefore, the sum from n equal 1 to infinity of n, and the sum of the monotonic divergent series of natural number is equal to the PSI value projected onto Q. Remember to always project on Q because we're dealing with a sum of integers, and is equal to -1/12. Of course, because that number is already a rational number, there's no need to project, but generally speaking, remember to project. Here it is, the proof number 4. Proof number 5, so Ramanujan summation. So let us apply now Ramanujan's summation method to find out the sum of the monotonic divergent series of natural number. Here is a formula, the sum from n equal 1 to infinity, and being a discrete variable of fn, f is a function, is negative the value of that function at 0, or -1/2 of it, minus the sum from m equal 1 to infinity of the even Bernoulli number b to m divided by 2m factorial of the 2m minus 1 derivative of f evaluated at 0. So again, where b to m is a 2m's Bernoulli number, actually 2m's plus 1, because we have b0, it starts at 0, the Bernoulli number, b0 equal 1. So strictly speaking, it's 2m plus 1 Bernoulli number in a context of b1 equal plus 1/2. Keep in mind, when you're dealing with Bernoulli number, you have two contexts, either corresponding to the value of b1, the second Bernoulli number. b1 equal plus 1/2 or -1/2. In this context, here of that formula, it's plus 1/2. So using fn equal n for n greater or equal than 0, what do we have? Fn equal n, obviously, f0 equals 0. The derivative of n is 1. It's a constant. So the derivative, the first f prime at 0 is 1. F second of n, the second derivative is 0. And of course, it's a constant 0. Therefore, the value at 0 is 0, and etc. And for the 2n minus 1 derivative of f evaluated at n is always 0. Therefore, when n equals 0, it is 0. And that formula is valid for any value m greater or equal to 2. So therefore we obtain the sum of fn, which is by replacing fn with n, which is the sum from n equal 1 of n, minus f0 over 2 minus b2 over 2 factorial f prime at 0. So in other words, only the first derivative is not equal to 0. Here it is. So now we can plug the values. f0 equals 0, f prime at 0 equal 1, so we are left with minus b2 over 2 factorial, which is 2, so minus 1/2 of b2. If we open the toolbox, just to remind ourselves how much is b1, that's the context we are in. b2 is always equal 1 over 6, so negative 1/2 of b2 is negative 1 over 12. Here we are. So that's proof number 5 using Ramanujan summation. Take us to the correct value of the divergent series, or sum of the monotonic divergent series of integers, of natural number. Proof number 6, Abel-Plana. So Abel and Plana are two mathematicians from Norway and Italy from the 19th century. So we're going to use their summation that they come up with a few years apart independently. So that's the formula, the Abel-Plana summation, which is a sum from n equal 1 to infinity of the value fn is equal to, it starts like Ramanujan summation, negative 1/2 of the function, the value of the function evaluated at 0, plus I, the square root of minus 1, from 0 to infinity of that expression. Keep in mind, that's a formula for a monotonic divergent series. If you take the formula, or if you're dealing with an alternate divergent series, the denominator will be different, will be a hyperbolic sign. So keep in mind which one you are using. Huh? So for f of s equal s, in that case s, that's a convention that we use a variable for a complex variable in a complex plane. So x for real, s for complex. F of 0 equals 0, obviously. F of it equal it, f of negative it equal negative it that we have here, and negative it is of course minus f of it, which means that the function is odd. So we obtain, if the function is odd, that will be twice the value of f of it in the numerator. So the sum of from n equal 1 to infinity of n is I, the integral of 0 to plus infinity of 2it, twice the value of f of it, because the function is odd, over e to the 2 pi t minus 1 dt. So here, let's use a trick. Let's add, so the I comes in front, I square becomes a negative sign, and then let's add pi on the numerator and 2 pi with a variable t. So we have added 1 pi here and 2 pi there, so therefore we have added 2 pi square on the numerator, so we add it in front on the denominator to balance out. So let's just use the Bose integral, which is defined as the integral from 0 to plus infinity of, in a u world here this time, u to the s minus 1 e to the u negative 1 at the denominator du. Now if you replace u by 2 pi t that we are after, so 2 pi t to the s minus 1 over e to the 2 pi t minus 1 d 2 pi t. So now that, by definition of the Bose integral, we can prove that it's equal to gamma at s times zeta at s, the gamma function and the Riemann zeta function at s. So now we need to use that formula for s equal to. Why s equal to? Because you can see the numerator, the power is 1. So if that needs to be equal to 1, s minus 1 equal to 1, therefore s equal to 2. So we apply that formula for s equal to, and therefore the value is gamma 2 times zeta 2 plus what we had in front, negative 1 over 2 pi square. So we open the toolbox, gamma at 2. So remember the gamma function, gamma of n is n minus 1 factorial. Keep in mind it's not n factorial but n minus 1 factorial. So gamma of 2 is 1 factorial, which is of course equal to 1. And the value of zeta 2 that we need here is the famous problem solved by Euler, the Basel problem. So I'm naming that constant pi square over 6, the Basel constant. So zeta of 2 is Basel. Basel, it's a town in Switzerland where Euler is from. So let's call that constant Basel. Gamma of 2 equal to 1, zeta of 2 equal pi square over 6. The pi square simplify, and we left with negative 1/2 over times 1 over 6, which is of course negative 1 over 12, which is the correct value. So we get to the correct value using the Abel-Plana summation method to get to the sum of the divergent series of natural numbers. The board here for the Riemann zeta function, that's a quick proof. So like we discussed on the previous proof, the Riemann zeta function, zeta of S, is defined as the sum from 1 to infinity of 1 over n, which is a discrete variable, to the s being a complex variable. So the sum of the monotonic divergent series of natural numbers corresponds to the Riemann zeta function evaluated at or with s equal negative 1. So the sum from 1 to infinity of n is therefore, as a trick, we can write it the sum of 1 to infinity of 1 over n to the minus 1 power, which is 1 over n brought on top, will come back to here. And by definition, if you compare that expression to this one, it's of course zeta of s for s equal negative 1. And that we open the toolbox. Do we have the value for that? Yes, it's a known value. Zeta function, Riemann zeta function at negative 1 equal to negative 1 over 12. So we just plug it here, and that gives us the result straight away. Quick proof, one line. Let's go to the last proof. Bigger board here for proof number 8, Dirichlet eta function. So the Dirichlet eta function, it is, you can see the Greek letter, it's like an N with a long leg here. It is basically the counterpart, the alternate counterpart of the Riemann zeta function. They mirror each other. The Riemann zeta function is like the monotonic version of the Dirichlet eta function. So it is, eta at s is a sum from 1 to infinity of negative 1 to the n minus 1 power over n to the ns. S being a complex variable. So the sum of the alternate, not monotonic, or the sum of the alternate divergent series of natural numbers correspond to the Dirichlet eta function evaluated with s equal negative 1. So we have that formula that gives us the value of the eta function for negative integers. So eta of 1 minus m equal 2 to the m minus 1 over m times the m, or m plus 1, Bernoulli number. M greater or equal to 1, which make those numbers 0 or negative. So Bm being the m's or m plus 1 Bernoulli number in a context of b1 equal plus 1/2. So for m equal 2 and b2, and knowing that b2 equal 1/6, we obtain sum from 1 into infinity of negative 1 to the n minus 1 power times n is equal, we just rewrite the n at the denominator, n to the n minus 1 power, which is by definition, again, comparing that like in a previous proof, with that expression, we can see it's identical for s equal minus 1. So it's eta at negative 1. So eta at negative 1, what it is, we just need to use that expression. We want the value at negative 1, we just need to take m equal 2. So 2 square, so it's 4 minus 1, it's 3 over 2 of b2. 3/2 of b2 we here. Knowing that b2 is 1/6, it will give us toolbox. b2 is 1/6, we plug it here, that gives us 3/12, therefore it's a quarter. So now we just use a functional equation linking the Dirichlet eta function to the Riemann zeta function, here it is, and we use that function for s equal negative 1 that we're already evaluating here. And that's simple, zeta at negative 1 is equal to 1 minus 2 to the square, so 1 minus 4, which is minus 3. Minus 3 zeta, we pass it on the other side, negative 1/3 of eta at negative 1. So negative 1/3 of 1/4, we have the expression there, becomes negative 1/12. And it's exactly what we are after. The sum of the monotonic divergent series of natural numbers is equal to negative 1 over 12, which is the value at zeta, Riemann zeta function at negative 1. We have seen it on the previous proof. So that's it. We went through 8 proofs that showing that the the sum of the monotonic divergent series of natural numbers is equal to -1/12. Proof number 1 was inconclusive. We didn't get to the result, and proof number 3 was incomplete, valid, but incomplete, because there is one portion we didn't prove where that adjusted intercept function is coming from. Otherwise, the 6 others are valid, so that gives you 6 proof of that formula for the divergent series. Thank you for watching. Bye.